Dear students, welcome to the 6th lecture of the course Electrical Distribution System Analysis. This is the first lecture of chapter 2nd, which is basically approximate methods of distribution system analysis. Before going to the chapter 2, we will just see what we have seen in chapter 1. In chapter 1, there were 5 lectures. In lecture number 1, we have seen various structures of the distribution system. Basically, we have seen distribution system is classified into primary and secondary distribution system. Then we have seen why we need to study distribution system analysis. And then finally, we have seen content of this particular course at the end of lecture number 1. In lecture number 2, we have seen various substation components starting from isolator, potential transformer, current transformer, circuit breaker, transformer, bus bar arrangements. In lecture number 3, we have seen various components of the feeder. We have seen voltage regulator, we have seen feeder configurations like single phase feeder, 2-phase feeder or 3-phase feeder. Then we have seen there might be underground cables. Then there might be sectionalizer switches, capacitor banks and all other components related to smart grids. In lecture number 4, we have seen nature of loads. In that lecture, we have studied various different kinds of load curves of different types of consumers, and we have studied various different factors like demand factor, load factor, diversity factor and utilization factor. And in lecture number 5, we have seen load allocation at the substation level, that is distribution transformer or feeder level. When we have measurement at the substation level, then we can allocate these loads at distribution transformer and feeder level. Now let us go to the approximate methods of analysis. If you do actual distribution system analysis, we have seen that in distribution system, lines are actually untransposed as well as loads are unbalanced. And we have seen that these loads might be of single phase, 2-phase or 3-phase in nature, and transmission lines also might be single phase, 2-phase or 3-phase. And if you want to do the distribution system analysis, exact modeling of all these loads as well as feeder components which might be single phase, 2-phase or 3-phase, we need to do detailed modeling. However, many times in the field, distribution engineers need approximate or quick kind of solution. So, what we are doing in approximate method, we are assuming that loads are balanced and lines are transposed. So, with this approximation, we can use single phase equivalent of your feeder as well as loads for the analysis. Let us take a simple example where we want to calculate voltage drop and how we can approximate this voltage drop. Let us see this figure. What I have done it here, you have this feeder component from say point 1 to point 2, which is having resistance of R and reactance of Jx, and then there is load which is having say lagging power factor. Voltage at load end is actually VL angle 0 and voltage at sending end say Vs angle delta. Now, if you plot the vector diagram or phasor diagram of this particular circuit, it is shown in this particular figure. So, since VL is having angle 0, so you have this VL vector here. Then if you add resistive voltage drop across the feeder, so this will be resistive voltage drop which will be in phase with current phasor, and then the voltage drop across your reactance will be with 90 degree with respect to your current, and if you add VL plus Ri drop plus Jxi drop, you will get voltage at the sending end terminal, which is basically this voltage Vs. Now, if you do exact analysis, your Vs voltage, that is Vs angle delta, will be VL angle 0 plus voltage drop across your feeder component, that is R plus Jx, which is feeder impedance multiplied by current, which is drop across the feeder. Now, if you can write in terms of rectangular coordinates, this Vs angle delta can be converted into Vs cos delta plus j Vs sin delta. Vs angle 0 as it is I kept, because it will not be having imaginary part. Then this I with phase angle minus phi, we can say I cos phi minus j sin I sin phi, and then there is impedance. Then if you multiply them and take the imaginary and real component together of this particular quantity, a real component will be IR cos phi plus IX sin phi, and imaginary component will be IX cos phi and IR sin phi minus IR sin phi. Now, we know that in case of distribution system, your angle delta will be having very small value. So, if the delta is small, your cos delta will be approximately equal to 1 and your sin delta will be approximately equal to 0. So, in that case, your imaginary component on left hand side and imaginary component on right hand side, they will be negligibly small. So, therefore, in case of delta which is small, we can say Vs cos delta will be equal to Vs, approximately equal to Vs, and then Vs sin delta will be approximately equal to 0, where these imaginary components are negligible. In that case, your Vs will be equal to VL, which is having only a real part, and then IR cos phi plus IX sin phi. Now, if you observe IR cos phi, so you are having this IR phasor here, and then you are having this angle phi, and this will be your IR cos phi length up to this one. And then if you see, since this and IR and IX, they will be at 90 degree, this angle also will be phi. In that case, this becomes your IX sin phi. So, this is same length. So, this also will be equal to IX sin phi. So, you can see that IR cos phi plus this IX sin phi becomes equal to real part of your phasor Z multiplied by I. So, if you see the real part of Z multiplied by I, it will be IR cos phi plus IX sin phi. Therefore, this IR cos phi plus IX sin phi, we can write it as a real Zi. Therefore, voltage drop we can see approximately we can write Vs minus VL, which is voltage drop between the two terminals, which will be equal to real part of Z multiplied by I. Now, let us check how much correct this approximation is. So, in that case, we can just assume some values for different components of this distribution system. Let us say Z12 is impedance of the feeder, which is given by this value. Then let us say current which is flowing through the feeder is having 43 ampere with lagging power factor of 0.9. So, therefore, phase angle will be minus 25.84, and if you see the voltages, voltage at sending end, I am assuming it is 2400 with angle 0 degree. So, if you calculate VL, that is voltage at terminal 2, it will be 2400, which is voltage at primary end, minus voltage drop across your feeder section, which is, this is your impedance multiplied by current, so Z multiplied by I. And if you calculate exact drop, so voltage at secondary terminal, that is V2, is 2378.41 with very negligibly small angle delta. So if you calculate drop from it here, which is VL Vs minus VL, so your Vs is 2400 magnitude we want to take, minus your VL is 2378.41. So exact voltage drop is actually 21.59. Let us say approximate drop, we have already seen approximate voltage drop is real part of Z multiplied by I. So say real part, your Z is impedance which is given, then current we have calculated, or which is given 43 amperes, and then from this if you calculate real part of Z multiplied by I, which comes around 21.65 volts. Now if you calculate error, so error will be equal to this value minus this value, this is real exact value and this is approximate value, and if you calculate error from this, so exact value minus approximate value divided by exact value, so error comes around minus 0.0028, which is very small, which is just 0.28%. So we can see that we can use real part of Zi as a voltage drop for realistic analysis of distribution system. Now come to the K factors. There are two K factors. One is called as K drop factor and another is called as K rise factor. Now K drop factor is nothing but percentage voltage drop across your feeder, which is of 1 kilometer length long, 1 kilometer long and serving 1 kVA load. So if you are having feeder section and if you are passing 1 kVA of power through this, and if the length is 1 kilometer, okay, then percentage drop which is happening across this length is called as your K drop factor. So K drop factor in that case defined as percentage voltage drop per kVA per kilometer. If your length of feeder is in miles, then you can write K drop factor will be percent voltage drop divided by kVA, and in that case it will be miles. So percent voltage drop per kVA per mile. Let us see how to calculate this K drop factor for a particular feeder section. Let us say your feeder is having geometry which is shown like this in the figure, where A, B, C are the conductors and these are the distances which are shown. So by knowing these distances, we can easily get your inductance of the feeder, which is just 2 into 10 raised to minus 7 natural log of GMD by GMR, where we know that GMD is nothing but cube root of all the distances, that is DAB multiplied by DBC multiplied by DCA, and if you take the cube root of this will give you GMD. And GMR is nothing but of particular conductor, which is nothing but, if it is single conductor, GMR will be equal to 0.7788 into your radius of the conductor. However, if the conductor is standard kind of conductor, then you can get the GMR from the data sheet of the conductor. Once you get the inductance, you can calculate the impedance of the conductor for 1 kilometer length by knowing the resistance of the conductor and inductance of the conductor. This will be impedance of 1 kilometer. Then we can calculate current for 1 kVA loading. So, current for 1 kVA loading will be 1 kVA divided by root 3 into line to line voltage, and its angle will be minus cos inverse of power factor. And therefore, once you get the current for 1 kVA load and impedance for 1 kilometer length feeder section, you can get the K drop factor, which will be real part of Zi divided by your V base multiplied by 100, which will be percent voltage drop for 1 kVA load and 1 kilometer length feeder. Let us see, for simple feeder how can we calculate this K drop factor. Let us say you are having impedance of the feeder, which is given here, Z is equal to 0.19 plus J 0.32 ohms per kilometer, which is impedance per kilometer. Let us say power factor of the load is 0.9, nominal voltage of the feeder is 11 kV line to line. In that case, your line to neutral voltage will be 6.35 kV. Then current taken by 1 kVA at 0.9 lagging power factor. So, we are calculating current for 1 kVA load. So, we know that current will be power divided by root 3 into VLL, and its angle will be cos inverse of power factor and minus sign since it is lagging. So, 1 kVA load and then voltage is line to line 11 kV and your power factor is 0.9. If you put those values into this equation, we will get value of current. We know the value of current at 1 kVA load, we know the Z for 1 kilometer. So, in that case, voltage drop for 1 kVA load and 1 kilometer feeder, we can calculate, that is the real part of your Z multiplied by I. Z is given, I is calculated. So, your voltage drop will be 0.0161. For K drop factor, we need percent voltage drop. So, to get the percent voltage drop, we need to divide this 0.0161 by base voltage. So, base phase voltage is 6.35 kV. So, we can put it here. So, K drop factor in that case will be 0.000254% drop per kVA per kilometer. Okay, let us see the application of this K drop factor. Let your K drop factor is 0.00254% drop per kVA per kilometer. Means you are having say feeder of 2.4 kilometer and the K drop factor of this feeder is 0.000254, and this feeder is supplying load of say 7500 kVA, and I want to estimate the voltage drop which is happening in this particular feeder section. So, you can get this voltage drop very easily. It will be your K drop factor multiplied by kVA multiplied by kilometers. So, K drop factor, kVA 7500 and length is 2.4 kilometer, which will give me 4.6% of voltage drop. And normally we know that there is maximum allowable voltage drop limits, and many times it may be plus minus 3%, plus minus 5% or plus minus 10%. Let us say for this particular utility your voltage drop limit is plus minus 3%, and I want to restrict the load such that this limit will not get violated. Now, I want to find out how much load I can serve without violating this 3% limit over this 2.4 kilometer feeder. That can be easily calculated here. So, load that can be served without violating limit of 3%. So, voltage drop limit is now 3%. So, V drop I can put 3%. Then K drop factor of this feeder we know, which I put it here, 0.000254, and length of the feeder is 2.4 kilometer. And from this we can easily calculate maximum kVA which can be served by this feeder, which is 4921.26 kVA. If the kVA is more than this, your voltage limit will get violated. So, we have seen two applications of your K drop factor, where in one application we have seen how to calculate voltage drop for different kVAs and different kilometer length feeder. Another application we have seen, if there is maximum allowable voltage drop limit, we can also calculate how much kVA we can serve from this particular feeder. Let us take one more example. Like I shown it in figure, this particular feeder, which is ranging from node N0 to N3, it is serving 3 loads with 3 distribution transformer T1, T2 and T3. The lengths of different feeder sections are mentioned here. So, first feeder section 2.4 kilometer, 1.2 kilometer and 0.8 kilometer, and 3 loads are 300 kVA, 750 kVA and 500 kVA. And let us say K drop factor of this particular feeder is 0.0002014%. And I want to calculate the total drop from point N0 to N3 if loading of my feeder is as given in this particular figure. This can be calculated as shown. So, for different feeder section from N0 to N1, we can see that whole load is flowing from N0 to N1. That is why total load flowing from feeder section N0 to N1 will be addition of all the 3 loads. Then load or power which is flowing from N1 to N2 will be addition of these 2 loads, that is 750 and 500 kVA, which will be 1250 kVA. And in third feeder section, only load which is flowing is 500 kVA. So, this gives us loadings of 3 different feeder sections. Length of first feeder section 2.4, second feeder section 1.2 and third feeder section 0.8. Then we can easily calculate voltage drops in all the 3 feeder section. In the first section, it will be K drop factor multiplied by kVA multiplied by your kilometer will give me drop in first section. In second section, again K drop factor multiplied by your kVA multiplied by your distance, that is 1.2 kilometer, which will give drop in second. Similarly, I can calculate drop in third section, and then if you add drops in all the 3 sections, I will get total drop in the feeder section from N0 to N3. So, drop from N0 to N3 will be 1.13%. So, this is the application of K drop factor. Let us see what is called as K rise factor. So, in case of K rise factor, it is basically applicable whenever you are connecting capacitor banks in your distribution system. So, let us see this particular figure. So, in this case also we are having the sending end and receiving end voltage, which is Vs angle delta and VL angle 0, then feeder impedance, and in this case your capacitive current flowing, because I am considering at the end there is capacitor bank. Now, if you analyze this circuit, we can see that the phasor diagram of this circuit is shown in the figure on the right hand side. So, this is your vector VL or phasor VL, and if you add two voltage drops, that is voltage drop across the resistance and voltage drop across the reactance, I will get voltage Vs. So, in this case, since it is capacitive load, your capacitive current will be leading with respect to your VL. So, angle between VL and capacitive load will be 90 degree. So, in this case also we can easily see that your real part of Zi will be nothing but your voltage drop. So, voltage drop, or in this case since your VL, which is voltage at the capacitor end, is more than voltage at the sending end, we instead of calling voltage drop we can call it as a voltage rise, which is again real part of Z multiplied by your current I. So, in this case it is capacitive current, and if you observe this figure, real part of Z multiplied by I, real part of this is nothing but your this vector, which is again exactly equal to your x multiplied by I cap. So, your voltage rise will be x multiplied by I cap. So, K rise factor is defined as percent voltage rise, because voltage is raising here, per kVAR of the capacitor per kilometer. So, voltage rise, percentage voltage rise per kVAR of capacitor per kilometer. If your distance is in mile, it will be percent voltage rise per kVAR per mile. Let us say impedance of your line is Z is equal to 0.19 plus J 0.32 ohms per kilometer. Nominal voltage of your feeder is 11 kV. Therefore, phase to neutral voltage or line to neutral voltage will be 6.35 kV. And in this case, we want to calculate current taken for 1 kVAR load, because we want to calculate K rise factor, which is basically percent voltage drop per kVAR per kilometer. So, to get current per kVAR, we need to calculate current for 1 kVAR. So, in that case your current will be given by this equation. This is nothing but your power divided by root 3 into VLL, and in this case since it is only capacitive current, your angle will be 90 degree. So, kVAR is 1 kVAR root 3 and then voltage is 11 kV line to line, angle is 90 degree. So, if you calculate this, your capacitive current will be 0.0525 and its angle will be 90 degree. Then we can easily calculate total voltage rise. Total voltage rise will be x multiplied by I cap. So, in this case we want I cap magnitude. I cap magnitude is basically 0.0525 multiplied by x is 0.32. So, if you multiply them, you will get voltage rise, which is 0.0168, and then K rise factor will be percent voltage drop. So, you need to divide this by base voltage, that is 6350. So, it will be K rise factor will be 0.0168 divided by 6350. So, if you do that, your K rise factor will be 0.000265%. That is, in this case I am saying percent raise per kVAR per kilometer. Now, let us take one example where we, as per example 3, we have seen that percent voltage drop for 7500 kVA load for 2.5 kilometer, means for this particular feeder length of 2.4 kilometers, and which is supplying 7500 kV of load, we have seen that the computed voltage drop is around 4.6%. Now what we want to do, we want to actually decrease this voltage drop by putting some capacitor across this load, and I want to calculate the value of this capacitor such that this voltage drop will be under the limit, which is, we have seen that plus minus 3%. So by putting the capacitor across this load, we want to increase the voltage so that the percentage voltage drop will be in limit of plus minus 3%. So to limit total voltage drop to 3%, the required voltage rise due to shunt capacitor bank is, so we want to increase, or we want to raise the voltage by 1.6%. So 4.6% is actual drop, and we want to improve it to 3%, then total of improvement in voltage is 1.6%. To improve this voltage, we would like to calculate the rating of the capacitor, which will improve this voltage to by 1.6%. The required rating of shunt capacitor is, then we know that K rise factor is percent voltage rise divided by kVAR divided by kilometer, and in that case total kVAR we can easily calculate, it will be percent voltage rise divided by your K rise factor multiplied by kilometer. So your kVAR of the capacitor can be easily calculated by this formula, which is percent voltage rise per divided by your K rise factor multiplied by your kilometer. So percent voltage rise is 1.6%, K rise factor is 0.00265, which is we have calculated in last slide, and the kilometer length of the feeder is 2.4 kilometer. So in that case your kVAR of the capacitor required is 2516. So we need capacitor of this size so that voltage limit will not get violated. Let us see the summary of this lecture. So we have started with chapter number 2, that is approximate methods of analysis of distribution system, where in this lecture number 6 we have started with K factors, and then we have seen two types of K factors. One is K drop factor and K rise factor and their applications. So we have seen that K drop factor is nothing but percent voltage drop for 1 kVA load for 1 kilometer. Similarly, K rise factor, we have seen that percent voltage rise for per kVAR capacitor loading per kilometer. Thank you.